Basically, we started with fluid mechanics last week for an hour, and then this week we'll be looking at hydraulics, applied fluid mechanics of water, and then move into more hydrology next week.
All right.
And typically we think about hydraulics in the two categories of pressure conduit hydraulics and open channel hydraulics. And that's the way we've got the notes set up and planning to proceed here, beginning with open channel hydraulics and then transitioning in an hour and a half or so into open channel hydraulics.
You just started.
Come on in.
We're up to 2.
We're looking for customers. When I was down there in person, I'd go out in the halls and bring them in.
Yeah, I seem to remember you left off, we just finished up on Bernoulli equation.
Yes, and that's where we'll start today.
All right.
And so, pressure conduit hydraulics is dealing with fluid flow of water in particular we're focusing on, and systems so that you're at something other than atmospheric pressure. That's as compared to open channel hydraulics of a little later this evening, where you've got a water surface at atmospheric pressure, a free water surface. And so what we're basically planning to do here is go down the list, and we're talking now about analyzing flows in pipe systems. And we're interested in discharge rates and pressures throughout the system. And we'll start with a pipe and look at flow in a single pipe. And the workhorse tonight will be the energy equation. We'll use the energy equation for pressure conduit flow and continue to use it for applications in open channel hydraulics as well. And one of the key terms in the energy equation is the head loss term. And so we'll look at the head loss equations. And after spending a bit of time with a pipeline, one pipe, we'll start looking at pipe systems and begin with 2 or 3 or more pipes where you got pipes in series and pipes in parallel, and then go on to complex networks, and then basically we'll get to the point where if you're doing a typical type application with say a municipal water distribution system, you may be talking about hundreds or even thousands of pipes in a typical Dallas, Houston, major cities water distribution system, and the basic concepts for the networks we're talking about in simpler systems are equally applicable there as well. And then last we've got listed here is pumps, and we'll incorporate pumps in the systems as we go as well. So I think we're ready to get started and jump into it, and you both should have your paper copies of what I'm putting on the television here as far as notes, and we'll go after it. The book, I didn't bring the book myself. Most of the topics that we're covering, not most of them, all the topics are covered in the Civil Engineering Reference Manual as well. I'll switch terminology a little here. They cover the pipes in the chapter on fluid dynamics, and I'm calling it hydraulics. And then they go into, as I recall, a separate chapter on open channel hydraulics. And they'll cover, of course, things in more detail in the reference material than I'll have a chance to do in the limited time here tonight as well. So, ask questions, bring up any points you want to discuss, and we'll go full speed ahead here. So we ended last time with the Bernoulli equation, and we'll begin with the equation. I'll call it the energy equation because it's more comprehensive. We're looking at head losses as well. And the basic terms are defined here. So anytime you're dealing with hydraulics, this particular page of notes you want to have memorized. It's really an accounting game we're playing here, in which we've got trade-offs between different forms of energy. And the diagram shows two sections in a pipe. We're calling one section 1, the other 2. And you've got elevation head plus pressure head plus velocity head at the upstream section 1. Likewise, you've got elevation head plus pressure head plus velocity head downstream. But you do have energy losses. As water flows, the turbulence of the water, the resistance of the pipe holding the water back causes some of that hydraulic energy to be lost to the environment as heat. And to us, as a civil engineer, that's an energy loss. It's lost for our purposes, and head losses are a key term. And so we've reproduced the energy equation here on the bottom of the sheet. Z1 plus the pressure head is the pressure over the unit weight of the water or the fluid, and then the velocity head is v squared over 2 times acceleration of gravity, 2g, and the subscripts 1 and 2 denote the upstream and downstream location of the section. And so the total energy upstream is equal to the total energy downstream plus the head loss. And I keep calling those terms energy, and they're a representation of an energy, but if you look at them, what are the units? We're looking at either feet or meters, and so that's really head, and engineers like to work in terms of head, and what head actually is energy per weight. It would be foot-pounds per pound of flowing water, or Newton meters per Newton of flowing water. And so that makes the units come out nicely. The elevation heads in meters or feet, and the pressure head is in meters or feet, and the velocity heads meters or feet. So head is usually more convenient to work with than energy itself in foot-pounds per pound or Newton meters per Newton. So basically a matter of trade-offs here. Oh, note the note at the top, the slope of the energy line. Well, let's also note the different components. Here's the pipe, the hydraulic grade line. Very common engineering term. We're in the engineering business always computing hydraulic grade lines. And by definition, that's the elevation head plus the pressure head. So if you've got the elevation plus pressure head, potential energy head at any location, and at all locations along the pipe, that's your hydraulic grade line. Now you take your hydraulic grade, add the velocity head to that, and you've got the energy line. And of course it's sloping because of the head loss. And so the slope of the energy line is just the head loss divided by the length of pipe over which that head loss is occurring. And we're interested in pressure. When you took a shower this morning, you were interested in having enough pressure to be able to have an adequate shower and so forth. And so this is just illustrating comparing pressure and pressure head. Basic formula from last week in fluid mechanics. Pressure is gamma H, unit weight of the fluid times the head, where the head's that vertical height of the fluid column or the water column above the point. And if we want to switch back and forth between pressure and head, and a lot of engineers memorize this, that 2.31 feet of head is equivalent to 1 psi. And so if you plug that into the formula, 1 psi, convert it to pounds per square inch, convert it to pounds per square foot, divide it by the unit weight of the water, and you get that 1 psi is equivalent to 2.31 feet. Pressures in municipal water distribution systems are typically between 60 to 80 psi, and so if you want to express that in feet, that's 139 minus 185 feet. Faucet pressures in your house, they're usually maintained above 5 psi, and so if you wanted to know the pressure and you hooked up your garden hose to your faucet outside and climbed up on the roof and saw how high the water rose in the garden hose, it would, the garden hose would be a piezometer, and it would show you how high the water would rise. And if you have 5 psi, it would be 11.5 feet the water would rise in that piezometer tube in that garden hose. Water mains, most cities try to maintain pressures above 35 psi. Atmospheric pressure, remember from last week, is 14.7 psi about, and that's equivalent to about 34 feet of water ahead. Okay, pop quiz time. Pop quiz. See if you guys are with me here. Where's the pressure the highest? At point A or point B? Got a vote for B? Did I? Everybody, we got a pipe here. It's horizontal, so the elevation head's the same. The flow from left to right, and the diameter of the pipe changes. And so intuitively, I like to ask this question because it illustrates that in hydraulics, things really aren't the way they seem intuitively. And I think, to me, B seems like the right answer intuitively, but it's not. It's the wrong answer. The answer is A, because we've got to go back to the energy diagram and think in terms of an accounting system, and it's just trade-offs between elevation head, pressure head, and velocity head. And so what happens, here's a formula you always memorize. Discharge is velocity times area. And so the flow rate's constant. There's no change in storage. It's just a pipe. Continuity says a constant flow rate. And so the pipe gets smaller. What's got to happen to the velocity? If the pipe gets smaller, the area gets smaller, so the velocity's got to increase. Now, the velocity increases, the velocity head, v squared over 2g, increases. So the velocity head at B is larger than the velocity head at A. The elevation heads are the same. It's horizontal. The pipe is horizontal. And so if you got a bigger velocity head here, and it's not coming from elevation head, there's only one other place for the trade-off to occur, and that's pressure head. And so if you got a larger velocity head at B, that means you got to have a smaller pressure head at B. And my point is that you've got to just view the energy diagram as a trade-off between the types of energy. And looking back at the energy diagram again, in this form we've complicated just a bit because we've added in a pump, and we've also changed...
Before you leave that...
Yes.
Before you leave that teaching point, what about you didn't mention the head loss between A and B. I mean, I understand your point that you did make the trade-off, but the head loss I would think would make that even a greater delta between A and B.
That's absolutely correct. That's a good point and a correct observation. But we know for sure that your point being that still makes A even larger pressure than B. And I'm assuming that in a short reach of pipe, the head loss may be relatively negligible. But even if we consider the head loss, it would make A having an even larger pressure than it would otherwise relatively to B.
Okay.
And again, we're playing with the energy diagram. We've got the pump in place now, and and notice what the pump does. It just lifts up the energy line and the hydraulic grade line, and so we add the term there. So we've got Z1 elevation. Section 1 is upstream. Section 2 is downstream. So we've got in Z1 the elevation head is just the vertical distance from some arbitrary datum that can be mean sea level or anything else we want it to be. And so elevation head plus pressure head plus velocity head plus the head added by the pump is equal to the corresponding energy downstream plus the head loss in between. And notice anytime you've got a constant diameter, the velocity stays constant, and so the energy line and the hydraulic grade line are parallel to anytime the pipe diameter is constant, the two energy line and hydraulic grade line is parallel. When the diameter of the pipe changes, the velocity head changes, and when you add the pump, everything just goes up, adding energy, adding hydraulic head. A real key to this equation is the head loss term, and that's where we're going now, is being able to estimate the head losses in the pipe. There's a couple of ways of doing that. Both ways are accepted. And for example, probably the most widely used of the water distribution system pipe network analysis computer software packages is the K-Pipe, the University of Kentucky Pipe Network Analysis Program. And using that software as an example, but other software as well, they'll have options to use either Dorsey-Weibach or Hazen-Williams. And all the textbooks will show both methods, and we'll talk about both methods as well. And so two approaches to doing the same thing, estimating head losses. Both are empirical equations. Dorsey-Weibach is more theoretically correct, and we'll point out the reason for that. And so we'll present it first. And so the Dorsey-Weibach equation says that the head loss is equal to an empirically determined friction factor F times the length of the pipe divided by the diameter of the pipe times the velocity head. The velocity head is V squared over 2G. And so your units, the head loss is either feet or meters, the length of the pipe and the diameter of the pipe, either feet or meters, and then that puts your velocity in feet per second or meters per second, and the acceleration of gravity, the G, is either in feet per second squared or meters per second squared, either English or metric units. And then the key term is this dimensionless friction factor. And one nice thing about Dorsey-Weibach, it is dimensionally consistent. Whatever units you use are fine as long as you've got consistency, unlike Hazen-Williams, which is not a dimensionally consistent equation. Key term is a friction factor, and that's an expression of the roughness of the pipe. And and the thing that makes the Dorsey-Weibach equation conceptually more correct than the Hazen-Williams, which we'll be looking at very shortly, is that the roughness coefficient is a function of both the fluid characteristics, the flow characteristics, and the pipe characteristics. And the flow characteristics are represented by the Reynolds number. The pipe characteristics is represented by the roughness of the pipe. And so this little epsilon is pipe roughness. And back in the old days, 30 years ago, when they were doing laboratory experiments, what they would do is glue sand on the inside of a pipe. And then this roughness was the height of the sand above the wall of the pipe. It's an average distance of the little roughnesses along the wall of the pipe is what it represents. And there are tables and all the references. This is the table that I Xeroxed out of the Civil Engineering Reference Manual, which you're using in conjunction with the review sessions. And for different types of pipe, it gives the values for roughnesses. And again, the physical meaning of this roughness is, of course, the roughnesses in the wall of the pipe vary, but it's sort of an average effective type of roughness height, distance measured from the wall of the pipe. And you can see how it can vary between smooth pipes and rough pipes. Welded steel, it says, ranges from 0.0001 feet to 0.0003 feet, and design values given. And so this type of information is available in in many different places, including the reference manual. We'll come back to this because it also gives the roughness values for the Hazen-Williams equation as well. This is the old Moody diagram. Yep, it is. And there were a lot of experiments made historically on establishing roughness coefficients for different type pipes and so forth. And finally Moody came along and took all the data and put it into this one diagram. And so we've been using this thing for decades now. It's in a lot of different references, a commonly accepted, widely used set of information. And so you estimate your F, your friction factor for the Dorsey-Weibach equation from this. If you're writing computer code, the different parts of the chart can be expressed in equation form as well. But for manual type computations, it's easy to just read the values from the graph. And so this is from the reference manual. I'm not sure why they cut the corners out, but usually you don't have the corners cut out there. But we've got the friction factor as a function of the Reynolds number. Now the Reynolds number is one of those several dimensionless numbers from fluid mechanics. And it's defined as the velocity times the diameter divided by the kinematic viscosity. And so as the Reynolds number gets higher, that means high velocity relative to viscosity. And so Reynolds number across the bottom, and then we've got relative roughness on one of the vertical scales. Relative roughness is the absolute roughness we just talked about divided by the diameter of the pipe. And there are different parts of the curve. Down here at the bottom, we call this a smooth pipe. And so the lowest line of all the curves is a smooth pipe. And what a smooth pipe is by definition is you have a laminar boundary layer covering the roughnesses. So if you remember laminar flow is when just one layer of fluid flows smoothly over another layer, as compared to turbulent flow where there's all kinds of turbulence and random motion of the fluid particles. And so at the wall of the pipe you have a laminar boundary layer. And smooth pipe means that the boundary layer is thick enough so that it covers up all the little roughnesses in the pipe, so that what the turbulent flow is actually seeing is the boundary layer, not the roughnesses. And so what that means is if you find yourself below the smooth pipe curve, you still just use the smooth pipe curve, that all the roughnesses are covered up by the laminar boundary layer anyway, and so the friction factor is not a function of the roughness. It's just a function of the Reynolds number. Now if you go out here far enough, what happens is that these lines are parallel. That means that the friction factor is no longer a function of the Reynolds number. Same friction factor for a range of Reynolds numbers, and it's a function only of the relative roughness, the roughness divided by the diameter of the pipe. And then you've got some area, we call that the fully rough, complete turbulent region. Then there's some area here in the middle in which both the Reynolds number and the relative roughness are instrumental in establishing the friction factor. And as far as solving problems, it's just a matter of computing the Reynolds number, dividing the relative roughness by the diameter, taking those two values, reading off the friction factor for use in the Dorsey-Weibach equation. Well, we need some numbers to plug into the equation, and so here's a set of numbers. An example problem for a given discharge of 1 cubic feet per second. We want to compute the head loss in 1,500 feet of new 6-inch diameter cast iron pipe, and I'm using roughness of 0.00085 feet. And if you refer back to the table 3.8 from the reference manual we were looking at a second ago, what does it recommend? 0.008 feet, and gives a range between 0.004 and 0.002 feet. And so you've got to pull this number off of whatever reference you're using. It's totally empirically determined from laboratory experiments. And so we're using the temperature of the water to get the kinematic viscosity from a kinematic properties of water table. Area of the pipe, 1/4 pi d squared to give you the area of a circular pipe to get the 0.196 square feet. The velocity is always the discharge divided by the area, a basic formula to memorize. And so the discharge is given as 1 cubic foot per second. We divide it by the area, 0.196 square feet, to get the 5.09 feet per second. We need that velocity to compute the Reynolds number. We also need the viscosity, the 1.217 times 10 to the -5 square feet per second, read from the table as a function of temperature. We plug those into the Reynolds number, the velocity, the diameter of the pipe, the kinematic viscosity, to get a Reynolds number of 2.09 times 10 to the 5th, which is one of the two numbers we need for the Moody diagram to estimate the friction factor, the other number being the relative roughness. So I use my 0.00085 feet divided by the diameter of the pipe of 0.5 feet to get a relative roughness. And so these two numbers we go to the Moody diagram with. And so you plug in the numbers on the Moody diagram. The Reynolds number is 2.09 times 10 to the 5th, and I'm reading it right there. So if you, on the bottom scale here, reading up this way to get the Reynolds number, the relative roughness of 0.0017, I'm reading on this scale, which is hidden in here, and that represents each of these lines. So what I'm finding is there's one line that says that the relative roughness is 0.0015. Right below it, right above it is 0.002, so 0.0017 is in there someplace, about halfway. So I come about halfway, and there's the point. So that's where I've got the relative roughness between the lines here. I'm doing a visual linear interpolation. I've got the Reynolds number, and so I can read across here to get the friction factor of 0.023. Okay, so we can take the number and plug it into the formula. I'm going to raise this just a bit. Our estimate of the friction factor of 0.023 from the Moody diagram, plug it in for F, plug in the given length and diameter of the pipe. We need the velocity head. We've computed the velocity above. Plug it in. Acceleration of gravity is 32.2 feet per second squared, and we estimate our head loss to be 27.8 feet. What you'd really like to do is to be able to calibrate pipes, and instead of using empirical data like the Moody diagram, and people will often do that in, say, a municipal pipe distribution system, if you can isolate sections of the system in which you can actually measure pressures and for given discharges, you can do calibration studies to estimate the roughness coefficients. Okay, the Hazen-Williams equation is another widely used equation for doing the same thing. And we've reproduced the equations here in the format that they're already in the form for the type work we're doing here with them, estimating head losses in a pipe. And so all the units, these are not dimensionally consistent equations in the sense that these constants have all the unit conversions lost in them. And so the length of the pipe needs to be in either meters or feet. The discharge needs to be in either cubic meters per second or cubic feet per second. The Q, the diameter of the pipe in meters or feet. And then we don't assign dimensions to the C. Now the C is a relative roughness. And the advantage of the Hazen-Williams equation, which is also the disadvantage in the Hazen-Williams equation, is that the C we normally treat as a function of the pipe characteristics only, whereas the counterpart, the relative roughness and the Reynolds number, are both used to compute the friction factor F in the Darcy-Weibach equation. So anyway, the equations expressed here in metric units and English units, they're identically the same, where the conversion factors are lost in the constants, and terms are defined. And I might mention in passing, the way you're looking, the equations you're looking at now are in a convenient format, and the way you'll typically use them for the application we're talking about, and that's the typical use, is to estimate head losses. But as you go through reference material, you'll see the Hazen-Williams equation written this way. This is not in your notes, and it's not critical to us other than to make the point, when you see the Hazen-Williams equation written in this format, it is the same equation. And this is in the same general format as we'll look at the Manning's equation when we get to open channel hydraulics. And so English units, the velocity is 1.318 times the Hazen-Williams roughness coefficient C times the hydraulic radius, which by definition is the cross-sectional area of the pipe divided by the wetted perimeter of the pipe, raised to the 0.63 power, and then the slope of the energy line raised to the 0.54 power. And then this is just rewriting it in metric units, which means everything's the same except the constant. Hydraulic radius is area over wetted perimeter. We could apply this equation to a pipe of any different types of geometry. It doesn't have to be circular pipe. And so when you write it in a more general form, the hydraulic radius can be for other pipe geometries, but for a circular pipe, the area is 1/4 of pi d squared. The wetted perimeter, that's the circumference of the pipe sides, that's pi d. So the hydraulic radius is always d over 4 for a circular pipe. We've memorized that Q is velocity times area, and we also recognize from the previous energy diagram that the slope of the energy line is a head loss over the length of the pipe. So if you put these expressions together into the Hazen-Williams equation and solve for the head loss, it takes you right back to these equations. And so we can see the Hazen-Williams equation expressed in different formats. Let's plug the numbers in again to illustrate the use of the Hazen-Williams equation. And so, same pipe as the previous example. We estimated head losses using the Darcy-Weibach equation. Same pipe, different equation. And so, if you go back to the table, it's in your notes. I don't think I'll put it up. Well, maybe I better. Let's go ahead and switch back. Here's a page we looked at just a couple minutes ago, and we were looking at the left-hand side at the roughnesses for use in estimating the friction factor F for Darcy-Weibach for the same pipe materials. On the right side here, we've got information empirically, laboratory determined information for the Hazen-Williams C factor. And it gives ranges, clean or new pipe, older pipe, and so you can make estimates from empirical data. You'd rather do calibration studies in the field for engineering applications, but you make these estimates, and of course taking an exam, you'll come to this type of a table and make an estimate of an appropriate roughness coefficient. And so we plug in the numbers.
Hey, small question for you.
Yes.
Somehow I've got, when I look it up in the book, I get C of 130.
Okay.
I just don't know if there's different tables or on. I mean, I know this is a small point, except I just wonder.
No, good point. And by looking up in the book, you're referring to table 3.8.
Right.
And you're saying that for the cast iron pipe, it says the range is between 150 and 80, which is a tremendous range. For a clean new pipe, it's 130. And for a pipe 10 to 20 years old, and what happens, you have built up deposits inside the pipe that makes it rougher than it was when it was brand new, so it drops the C value. And so a brand new clean pipe, 130 would be a good number. As the pipe gets older, it would drop toward 100. And so I didn't know which number to use, so you'll notice I've worked the problem twice, once with 120, then once with 130 to see how much difference it makes.
Yeah, you just, all right.
Just to sort of test the sensitivity.
All right, great.
And so you plug in the numbers, and the numbers are all the same, except the first time I plugged in 120, which is a reasonable number for a pipe that has been in the ground for a while. And then I plugged in 130, which is a reasonable number for a brand new pipe. And the head loss up here is 29.3 feet, and the head loss here is 25.2 feet. And I forget what it was before. It was some number in between those two numbers when we applied the Darcy-Weibach equation. Okay. Before we get down the road too far, what's going to start happening is our pipe systems are going to get more and more complicated, where we're looking at several pipes, and we're going to find that it's for convenience. It's nice to be able to just express the relationship between head loss and discharge simply as the head loss is some K times the discharge raised to some power. Now, depending upon whether you're using the Hazen-Williams equation or the Darcy-Weibach equation, in the Hazen-Williams equation, the power is going to be 1.85, and in the Darcy-Weibach equation, the power is going to be 2. And this is sort of a handy little table that sets this up. I'm coming back to this in just a second, but let me divert and just illustrate using Darcy-Weibach. So I've thrown in an extra page here, and just in the case of the Darcy-Weibach equation, which I've reproduced here, and the head loss is friction factor times L over D times the velocity head. We can also, knowing that V is Q over A, substitute Q over A in for V and write it this way, and then having written it this way, we can just rearrange it so that the head loss is all of these terms times Q squared. And so what I'm saying is all of this stuff lumped together is K. And then Q is raised to the second power. And so for either Hazen-Williams or Darcy-Weibach, with Darcy-Weibach the end's 2, with Hazen-Williams it's 1.85, and depending on what unit you're using, the K is going to be these expressions. And so what that allows you to do is take the characteristics of the pipe and reduce the length of the pipe, the diameter of the pipe, the roughness of the pipe down to one number at the very beginning, and then work with that. And you may have many pipes, and so you'll represent each pipe by K. Everything that I've said so far regarding head losses applies to head losses in a simple reach of pipe, a length of pipe that's just a straight length of pipe. Now, in addition to that, pipe systems have valves and fittings and bends and expansions and contractions and all kinds of fittings. And any head loss is caused by a turbulence. Any additional roughness, anything that causes more turbulence is going to increase the head loss. And so in addition to the pipe itself, we've got all these fittings. And we call them minor losses. Minor losses might be quite major, or they might be minor, depending upon the relative magnitude of how many fittings and the impacts of the fittings compared to the lengths of the pipes in the system. But we do consider minor losses, and there's empirical information to help you do that. I've Xeroxed this particular page of notes out of the reference manual again, and this is a typical way of doing it. Just say the minor losses are some empirically determined coefficient K times the velocity head. And then you need to estimate the K, and to estimate the K, for example, from the reference manual, they use this formula, and this can be expressed different ways, but for an enlargement, here's a formula to estimate the K. The K, the minor loss coefficient, is 1 minus the diameter upstream divided by the diameter downstream, d1 over d2 squared, and then square the whole term. Sudden contractions, it gives an equation, and it's just giving some basic information based on empirical data to estimate minor loss coefficients. At an exit, it's saying the coefficient is 1. Pipe entrance, for sharp edge entrance, K of 0.5. And for rounded entrances, it gives some additional information. Another thing that's quite common is to express losses in terms of equivalent pipe. As a matter of fact, the general concept of equivalent pipe has broad applicability. I'm actually expressing it here in terms of minor losses. And, well, let's do that. By definition, what an equivalent pipe is. And that's if you've got pipes, fittings, or pipe systems are equivalent if they have the same discharge versus head loss relationship. Now, head loss is K times Q to some power. And so if you've got one system that's pipes and fittings and so forth, and it's equivalent to another single pipe, it means that for a given discharge, the head loss is the same. And we can do that with minor losses. And so to do that, I've expressed minor losses, the head loss due to the valves, the fittings, the bends, the contractions, expansions, etc., is a loss coefficient associated with that fitting times the velocity head. And we've gone through this already. The Dorsey-Weibach equation says that the head loss in a straight section of pipe is that friction factor F from the Moody diagram times L over D times the velocity head. And so by definition, equivalent means that the head loss discharge relationship is the same between the pipe and the minor loss. And so for a given Q, the same Q, the minor loss is equal to the head loss in the pipe. And so the head loss in the minor loss in the valve or the fitting is just Km times the velocity head, and for the same discharge, the velocity and area of the velocity head is the same, and in the equivalent pipe, it's FL over D times velocity head, and so what that means is Km is equal to F times L over D. Km representing the fitting, F times L over D representing an equivalent length of pipe, and so what we can do is take the K for the fitting, the valve, the diameter of the pipe, and we're assuming the same diameter in the fitting and the valve, the friction factor in the pipe, and that L is a length of pipe that's equivalent to that valve, or to that fitting. Now, using the same concept, it's applied quite often. Say you're doing the water distribution system for Fort Hood, and there's several 1,000 pipes in the system. And to simplify the analysis, what you can do is isolate sections of the system and replace them with an equivalent pipe. And people often do that to simplify their systems. Maybe they'll take all the pipes less than 3-inch diameter and replace them with an equivalent pipe. And but that's another application. But the application we're pointing out here for equivalent pipe is to represent in the computations a valve or other fitting as being equivalent to a length of pipe, and then you can just add that length of pipe onto the pipe that's already there. And I've Xeroxed this out of the reference manual as well, but this is just showing some equivalent lengths of pipe for some different fittings. And so this is just another way of expressing minor losses. And so the two ways we've looked at is the concept of an equivalent pipe, a length of pipe that gives the same head losses for a given discharge as that particular fitting or group of fittings. And then the other way is to express it as the minor loss being a minor loss coefficient times the velocity head. Okay, here's a classic problem from fluid mechanics. We've got flow from from one reservoir to the other. The difference in water surface elevation is 30 feet. It gives us a chance to apply the energy equation, so we reproduce the energy equation there. Well, what we're computing here is the flow rate, the discharge between the reservoirs, and the pipe characteristics are given. We've got a 6-inch diameter, 500-foot long steel pipe, relative roughness 0.0017 feet. We're conveying flow between two reservoirs, which have the indicated difference in water surface elevation, entrance and extra or squared edge. That'll help us to estimate the minor loss coefficients. We compute the flow rate. If you pick a couple of points, let's say pick this point in the water surface and this point in the water surface, and call this point 1 and call this point 2. You write the energy equation between those 2 points. We're using gauge pressure, meaning atmospheric pressure is 0. We need some datum, and it would be convenient just to call this our reference datum for elevation head. And if we do it that way, then that means Z1 is 31. The elevation head at point 1 is 30 feet above the reference datum. The pressure is atmospheric pressure, which is 0. We're using 0 atmospheric pressure as our reference for gauge pressure. We're assuming the reservoir is big enough, there's no flow of water, so the velocity head's 0. Z2 is 0 by virtue of the way we've defined our reference datum for elevation. P2 over gamma, pressure head is also 0, it's atmospheric pressure. Velocity is 0, and so the only thing left is head loss. So what we just said is anytime you're dealing with the classic problem of a pipe connecting two reservoirs, the head loss is just the difference in the water surface elevations between the two reservoirs. So the head loss is 30 feet, and we'll use that information, take it forward. We want to compute the discharge, the flow rate in the pipe, and so we choose to use the Darcy-Weibach equation. Could have used the Hazen-Williams just as well. And here's the Darcy-Weibach equation. Reproduced it here. We need to estimate a friction factor F, and this is what we know. We can estimate the roughness from the table, 0.0015 feet. The diameter of the pipe is 0.5 feet. We've got 0.003 as a relative roughness. Now the friction factor also depends upon the Reynolds number. There lies the advantage and the disadvantage in the Darcy-Weibach equation compared to Hazen-Williams, in that the friction factor is a function of flow characteristics as well as pipe characteristics. And the problem is we don't know the flow. That's what we're trying to compute, so we cannot compute the Reynolds number. And so when I say I assumed F is 0.016, that's not a complete guess. I do know the relative roughness, but I'm trying to compute the discharge, so I don't know the Reynolds number, but I can look at the Moody diagram, and if you look at the Moody diagram for this relative roughness, it puts you in the right vicinity on the Moody diagram, and you can make an educated guess of what F ought to be. And so it just meant that I'm not sure what it ought to be. So when I finish solving the problem and I know the discharge, then I got to come back and check it. And so we'll just remember to come back and check our initial estimate of F. Plug in the 0.016 for the friction factor, plug in the length and diameter of the pipe. So it's the velocity head we're computing. Now this head loss is the head loss in that 500-foot long length of pipe. And so when you run these numbers out on your calculator, you get the head loss is 16 times the velocity head. There are additional head losses. We've got the entrance losses and the exit loss. And from the previous page, which I Xeroxed out of the reference manual, it says that for an exit, the head loss coefficient is 1. And you can sort of visualize that. If you think about it, if you got a pipe emptying into a big reservoir, as the water flows into the reservoir, what proportion of the velocity head is lost? you're going from some significant velocity in the pipe to essentially zero or still tranquil water in the reservoir, so you're losing all of the velocity head. And so the coefficient's 1. We're just losing the velocity head as we exit into the downstream reservoir. And then the table tells us that for a squared-edged entrance loss coefficient of 0.5, we're using that. And so that tells us our minor losses are 1.5 times the velocity head. And so when you add the losses in the pipe, the 16 times velocity head, plus the minor losses, 1.5 times velocity head, you get 17.5 times velocity head. And we already know that's 30 feet, the difference in water surface between the two reservoirs. Everything in that equation we know acceleration of gravity is 32.2 feet per second squared, so we solve for the velocity head, or solve for the velocity to get 10.5 feet per second. And I did make this estimate because I didn't know the velocity. Now that I know the velocity, I can come back and check it to see if the friction factor is 0.016. I take the velocity, plug it into the equation for the Reynolds number, and get a value of 4.3 times 10 to the fifth for the Reynolds number, and then taking that in combination with that relative roughness of 0.0003 feet, go back to the Moody diagram, and I won't go put the Moody diagram back up again, but you can plug in those two numbers and read off a friction factor, assuming I read it off correctly, of 0.0164. I assume 0.016, and that's close enough for me. I don't want to do it over again. But if this would have come out to be 0.018, then I would have taken the 0.018 and reworked the problem again. The nice thing about Hayes and Williams from working problems is it's not the roughness coefficient is not a function of the flow characteristics. Of course, it's not theoretically as correct either, because the friction roughness coefficient should be a function of the flow characteristics. The problem actually said compute the discharge. We computed the velocity, so you multiply the velocity, the mean flow, that's a mean velocity in the pipe, times the area through which that velocity is flowing to get the flow rate of 2.06 cubic feet per second. Same problem again, let's just put a pump in it. I want the water to go the opposite way. And the only way I can get the water to go the opposite way is to install a pump. And so we add a pump to the system, the flow direction's reversed, and the question is what pump head is required for a discharge rate of 2 cubic feet per second. We want to pump 2 cubic feet per second from the lower reservoir to the higher reservoir. We need the area of the pipe. 1/4 pi d squared will give you the area of the circular pipe. We need the velocity. The flow rate of 2 cubic feet per second is given. We know that divided by the cross-sectional area of flow gives us a velocity of 10.2 feet per second. And we don't really need to repeat the head loss versus velocity head computations. It's the same as the previous problem. So I've just reproduced the results from the previous problem. Remember, the head loss is 17.5 times the velocity head. And in this problem, though, we've got the discharge given, thus the velocity. So we plug in the velocity, we get the head loss of 28.2 feet. And our old friend, the energy equation, which we use over and over in hydraulics. And we plug in our estimate for the head loss. And we plug in everything else. We're going backwards this time. So I'm letting subscript 1 be the downstream reservoir, which is on the right in the figure. Subscript 2 be the upstream, the higher reservoir, which is on the left in the figure. And plugging in the 0 and 30 for the elevation heads at the two places, the 0 at both places for the atmospheric pressure head, the 0 for the velocity heads, and we get the head in the pump, and it's going to always come out to be this. We'll do some more pump problems, but what the pump's doing, it's lifting the water 30 feet, but it's also having to overcome the head losses in the system. And so the head to be supplied by the pump is 58.2 feet, including both the lift it has to overcome and overcoming the head losses. Okay, power and energy. While we're talking about pumps, we can talk a little bit more about pumps. Of course, energy is the ability to do work. Work is force through a distance. Power is the rate of transferring energy, or it's the work per unit time. And so if you think in terms of power being energy per time, which it is, and you can think in terms of if you got a weight per time, and remember unit weight, that's gamma here is a weight per volumetric flow rate, and then Q is a volumetric flow rate. You multiply those together and you got a weight per time. Head is energy per weight, and so that's power, and that's the power equation. Power is gamma times Q times H. H is the head, Q is the discharge flow rate, volumetric flow rate, gamma is the unit weight of the water. The units we tend to use kilowatt, which is a kilonewton times a meter divided by a second, kilonewton meter per second. A horsepower in the English system is 550 foot-pounds per second. A conversion factor, 1 horsepower is 0.746 kilowatts. And continuing with this same train of thought, actually in the power equation, when you're converting between energy, with a pump, we're converting electrical energy to hydraulic energy. Of course, we could also be talking about a turbine where we're converting hydraulic energy to electrical energy, but there's always some loss of energy. There's never 100% efficiency. And so we'll add in the efficiency, and the efficiency is the ratio of the electrical energy going in to the hydraulic energy coming out. So it's a number less than 1. And here we've got the power, and the units in kilowatts or in foot-pounds per second. We got the unit weight and the kilonewtons per cubic meter, or pounds per cubic meter, discharge rate in cubic meters per second, cubic feet per second, the head in meters or feet, and the efficiency. And a common term is brake horsepower. In the English system, people historically got involved in the term horsepower. And of course, a horsepower is 550 foot-pounds per second. But if you write the power equation and are working in units of horsepower, you can plug in the unit weight of the water in terms of pounds per cubic feet, the discharge rate in cubic feet per second, the head provided by the pump in feet, and then this conversion factor 550, and of course dimensionless number less than 1 representing the efficiency in converting from electrical energy to hydraulic energy. The next example says plug the numbers into the equation, and so this gives us some numbers. And so it says in the previous problem, determine the horsepower required for the pump to do what we asked it to do in the previous problem. And what we asked it to do in the previous problem was to pump 2 cubic feet per second against a head of 58.2 feet. And now we're saying our pump, the manufacturer is telling us that the pump has an efficiency of 0.75. And so we can plug in the numbers, the unit weight of water, 62.4 pounds per cubic feet, and the flow rate, the head, the conversion to get to horsepower from foot-pounds per second, the efficiency, and we can say we need 17.6 horsepower to run that pump. Okay, how are you guys doing? Would you rather take a short break now, or say go 30 minutes and take a longer break? Got a preference there?
You drive on. You're doing good.
Let's do it then. Well, we're talking about pumps, and we'll continue to talk about pumps as we go. But here's a problem that is sort of a classic, typical type of engineering problem, and that goes back to the fluid mechanics session when we were talking about atmospheric pressure and gauge pressure. And what happens is, on the suction side of a pump, you can drop the pressure well below atmospheric pressure. Now, if you drop it enough, if you drop it all the way to vapor pressure, you can have the water to start vaporizing. That's called cavitation. And what happens is you get vapor bubbles form because the water is converting itself to gas, to vapor. And it can be a real problem because then the vapor bubbles go into the pump, and then actually most of the damage is done when they turn back to water and sort of implode, not explode, but implode, and they can damage the pump and they block the flow and so forth. And so there's a physical limit of zero pressure, but there's also a practical limit of vapor pressure when the liquid water starts getting vapor bubbles in it. And so what's going to happen, the higher you get the pump, you know, we're trading energy. And so if you think in terms of some point here, and the total energy head here compared to the energy head downstream of the pump, if the pump's higher, the higher this gets, the lower the pressure has to be. And the larger, and you also have velocity head, so the trade-off is velocity head, pressure head, and elevation head. So if you have a large discharge rate, you got a lot of velocity head, and that's coming out of the pressure head. If you raise the pump higher, you've got a lot of elevation head, so that's coming out of pressure head. So what I'm attempting to say is, for a given elevation, there's only a certain discharge you can get through the pump. Or to say it another way, for a given discharge, there's only so high you can raise the pump above the water surface. And so, and for example, if you're trying to pump water over a levee, say the sump behind the levee, you want to pump the water over the levee into the river, or any application where you're pumping water up, it can only go so high for a given discharge rate. So anyway, this example illustrates that. It says compute the discharge rate that causes the pressure to drop to vapor pressure. The pipe between the reservoir and pump has a length of 1,000 feet, diameter 3 feet, and friction factor F, which I misspelled the word. You need to correct my spelling in your notes there, and also my little degree sign. 0.02, so that's implying we're using the Darcy-Weibach equation, and the temperature of 80 degrees Fahrenheit will give us the vapor pressure. Vapor pressure is from the properties of water table in the reference manual. And so here's the data. This is what we know that we'll need to work the problem. Atmospheric pressure at this location on the Earth is 13.8 psi, which converts to 1,987 pounds per square foot. The vapor pressure for this temperature is 0.51 psi. That's pounds per square inch using absolute pressure as a reference. And so that's 73.4 pounds per square foot. The unit weight of the water is 62.22 pounds per cubic foot. And we need to be able to express head loss as a function of discharge, which is same as velocity. And so Darcy-Weibach equation we've written here, we plugged in the friction factor F, we plugged in 1,000 feet, we plugged in 3 feet for the length and diameter, and we plugged in the numbers, and so we get the head loss is 0.119 times the velocity squared. So we can take all this information and figure out the maximum discharge rate in which we can pump through that pump before cavitation or before the vapor bubbles start to form. So we write the energy equation again, and between point 1 and point 2. And so the pressure, we're not using gauge pressure. On almost all of our applications we use gauge pressure. And this is an example of when it's more convenient to use atmospheric pressure. And so the atmospheric pressure is the 1,987 pounds per square foot. And so that's going to be the pressure here. Now the worst case scenario is we're dropping to vapor pressure here, and so the vapor pressure is 73.4 pounds per square foot, and we can draw the reference datum wherever we like. We'll just draw it at the water surface here, and we'll plug in the numbers. 0 for elevation head, the atmospheric pressure over gamma for the pressure head, 0 velocity in the reservoir. And then the pump is 10 feet higher, so Z sub P is the elevation of the pump above the water surface. The pressure head just downstream of the pump is where we've defined our point 2. The velocity head in the pipe at the suction side of the pump, and then the head loss. And so we plug in all the numbers, and we've got an expression for the head loss from the Darcy-Weibach equation from the previous page. We plug that in. And when you plug in all the numbers, everything's known except the velocity. And so we solve for the velocity. And so the velocity is 13.2 feet per second, and we can multiply by the cross-sectional area for the pipe to get the flow rate of 93.3 feet per second. And so for that 10 feet, we can pump 93.3 feet per second, cubic feet per second, and when we get around that vicinity, that's when we start getting into problems with cavitation. Now, if you set the discharge, you could, another problem, a good exam problem would be for a given discharge, how high can you make the pump? Same thing, you're just solving for the Z instead of the velocity in that variation of that particular concept. As a matter of fact, on the next page of the notes, this is sort of a general problem that you can see. So I've instead of using a specific set of numbers, I've just repeated the problem in general, and so you can solve any problem involving pumps and how high they can be, or the discharge rate that they can be at before the cavitation problem occurs. So you just write the energy equation between point 1 and point 2. Having written the energy equation and defining the reference datum at the water surface, you can then plug in 0 for Z, and then for Z2 is the elevation of the pump above the water surface. You plug in atmospheric pressure, and then you plug in vapor pressure. You plug in 0 velocity head in the reservoir, assuming it's big enough where the velocity is very small, and you plug in the velocity head in the pipe, and then you plug in an expression for the head loss, and then you can just rearrange that to come up with the general formula that could be used for the example we just worked, or any problem like that. Okay, I've got another question for you. Pop quiz coming up. This is another one of those things that illustrates that things aren't always what they obviously you might guess them to be. And so we've got a situation here where we've got the discharge from a pipe. The flow split into two pipes. I'm calling this upper pipe Pipe A and this bottom pipe Pipe B. And so it flows through the two pipes, and then the pipes join, the flow continues. And my question is, which pipe has the greatest head loss? Pipe A or Pipe B? And then I've described the pipes. This pipe has a large diameter. It has a relatively short length, and it's a PVC pipe. That's a very smooth pipe. The roughness is a very small number, 0.000005 feet. If you were using, you would use that for the Darcy-Weibach equation. If you were using Hayes and Williams, it would be a very smooth 140 feet. And then this pipe is small diameter relative to this other pipe of 1 feet. It's longer, 150 feet. It's rougher. It's cast iron with a roughness of 0.0008 feet. And so we've got a large diameter, short, smooth pipe. We've got a small diameter, longer, rougher pipe. And my question is, which one has the largest head loss?
Well, you already gave it away.
Mm-hmm. Okay. Well, which is it? And you're pretty well guessing it's not the obvious answer.
Well, it still seems that you'd take that epsilon over D relationship, and that would be the driving factor. You know, depending on how those two.
Yeah, and so what that would mean, though, you've got a smooth pipe with a large diameter, and so a smooth pipe with a large diameter means, intuitively, it means little head loss. Where
right.
Here you've got a smaller diameter, rougher pipe, and so epsilon.
It should be more head loss.
Right, and so the obvious answer would be the very incorrect answer, the obvious answer would be pipe B. would have the greater head loss. But that's
Yeah.
wrong. What's right?
Is that because there's not much flow goes through that pipe?
That's exactly correct. The head loss will be the same in both pipes.
Oh, it has to be, doesn't it? Because
You
the
got-
pressure is the same on each end.
You've got some head there, right?
Oh, you're so mean.
You got some head there, right? The head loss is the difference in head between there and there. So if you go this route, there's some difference in head, is it not? If you go this route, there's some difference in head. It's the same. And so, as Lee just pointed out, what is going to happen? What does Mother Nature, what does the physics of the problem know? The physics of the problem knows that the head loss is KQ to some power. And so what it's going to do, the pipes are going to have different discharge rates. The flow is going to be split in such a way that the head loss is the same in the two pipes. And that takes us into the topic of multiple pipe systems, and we can talk about pipes in series and pipes in parallel. And the basic relationships are given here. If you got pipes in series, pipes 1, 2, and 3 are back-to-back in series, and so the discharge in this system is equal to the discharge in pipe 1, which is equal to the discharge in pipe 2, which is equal to the discharge in pipe 3. You got a discharge rate which is constant in all three pipes. Now the head loss, if you want to go from one end of the system to the other, from this end of the system to this end of the system, the head loss is just the head loss in the first pipe plus the head loss in the second pipe plus the head loss in the third pipe. A few minutes ago we talked about the concept of an equivalent pipe, and you might even want to use that in a practical problem. Say you had a very complex system and this is just part of the system. You've got the water distribution system for Fort Hood, and it has thousands of pipes, and you want to simplify the problem. You could replace that with one equivalent pipe. And when you're, say, using the KY pipe water distribution system simulation model. And so if you did that, you would say the head loss in the equivalent pipe, and the equivalent pipe is just one pipe equivalent to all three of those, would be that total head loss. And so you would have a K, and the head loss is K times Q to the N. And so the head loss in the equivalent pipe would be the K in the equivalent pipe times Q to the N in the equivalent pipe. And the head loss in the first pipe is just its K times Q to the N. Second pipe, it's K times Q to the N. The third pipe, it's K times Q to the N. So you add those three head losses together, and we're saying the same head loss for a given Q, so all the Qs are the same. And typically, you'd have the same N. If you're going to have, you apply Darcy-Weibach to all the pipes, N would be 2. If you're going to apply Hazen-Williams to all the pipes, N would be 1.85. And so the equivalent K is just adding the Ks together. That's for pipes in series. For pipes in parallel, here we've got pipes 1 and 2, which are parallel to one another. We could have any number of pipes parallel to one another. And so the flow rate is just, the total flow through the system is the discharge in pipe 1 plus the discharge in pipe 2. The head loss from here to here is equal to the head loss in pipe 1, which is also equal to head loss in pipe 2. If we wanted to go through the same exercise to come up with an equivalent pipe, we would recognize that head loss is K times Q to the N. We'd solve for Q out of that equation, which is head loss over Q raised to the 1 over N power. And then we would say that the total Q is equal to the Q in the first pipe plus the Q in the second pipe. And then we'd plug in that expression for the Q, and that would be the Q in the equivalent pipe. And again, the equivalent pipe would be one length of pipe that would be equivalent to this pipe system that we're looking at. And so that's a Q in the equivalent pipe using that expression, the Q in the first pipe using the expression, the Q in the second pipe using the expression. And so that gives us an equivalent K, an expression that gives us an equivalent K as a function of the K for each of the two individual pipes. If we did want to come up with an equivalent K to replace that pipe with an equivalent pipe for computational purposes. just taking the basic concepts that are expressed on those 2 pages of the notes and working some problems with them. And so here's the same problem before, or a similar problem, where we're connecting that reservoir that has a 30-foot difference in water surface elevation. The only difference is that it's being connected by 3 pipes in series. And so the problem is compute the discharge through the pipes. And we went through in a previous example and looked at writing the energy equation between a point in the water surface here and a point in the water surface there. We could do it again, but what it's going to come out to is that the head loss is 30 feet whenever you're connecting 2 reservoirs. So we know the head loss is 30 feet, and that's the total head loss. We're going to simplify life just a bit by neglecting minor losses. We could have included those. If you got real long sections of pipe with relatively smooth fittings, the minor losses are going to be negligible anyway. And so on the sheet here, the lengths and diameters of the 3 pipes are given. The roughness, we're using cast iron pipe in all cases, and we got the same roughness, but the relative roughness changes with diameter, and so we can compute a relative roughness. And from that, we got the same problem as we've had before. I'm using Darcy-Weibach equation, and so to estimate the F, I've got to know the velocity to compute a Reynolds number. But it's the discharge we're trying to compute. We don't know the velocity yet. So same thing in that I do know the relative roughness is, but I don't know the Reynolds number. But it's not a complete guess. It's a very educated guess knowing the relative roughness is. So going back to the Moody diagram, I made these estimates for the friction factor for each of the 3 pipes. And then the area of a pipe is 1/4 pi d squared. We can plug in the diameters and get the areas of the pipes. And then we need an expression for head loss. And the head loss is KQ to the N. This is Darcy-Weibach equation, so the N is 2. And we need the K, and the K is just all these terms in the Darcy-Weibach equation, so we can plug in the values we know for each of those, including this estimated F, and express the pipes and Ks. So everything we know, the length and diameter and our estimate of the F for each pipe is embedded in the K for the pipe. And the K is head loss is K times Q squared. And so given that information, we just use a bit of ingenuity. Every problem can be different as far as this general category of pipe flow problems, and you've got to just use a bit of ingenuity in conjunction with those basic fundamental relationships. And so one relationship is pipes in series. If you got pipes in series, and I won't flip back to the diagram, but you can take a look at the diagram. And we've got the 3 pipes in series, so the discharge is in each of the pipes the same. So now with pipes in series, the head loss is the total head loss between those 2 points in the water surface in each of the 2 reservoirs, which we know is the 30 feet. It's the head loss in the first pipe plus the head loss in pipe 2 plus head loss in pipe 3. We know that head loss is K times Q squared. We know that the Q's are the same, so that Q is a constant. We know the K's, so we plug in the K's, and the only thing we don't know is the Q, so we solve for the Q. And we got the flow rate in the pipe system. But I remembered in a lot of problems we sort of are given an F, and in a professional engineer's exam they may actually give you F, and you don't even have to go back to check it. But since I estimated them not knowing the velocity, now that I know the discharge divided by the areas of velocity, so I can compute the velocity in each pipe. Given the velocity, I can compute the Reynolds number in each pipe. Now I know the Reynolds numbers. At least I know the Reynolds numbers for that flow rate of 8.76 cubic feet per second. So given the Reynolds numbers for each of the pipes, given the relative roughness from each of the pipes, which I knew from the very beginning, I can go back to the Moody diagram and get an estimate of F. And they came out almost the same. Being a little lazy in making the notes, they were close enough that I didn't want to work it over again. But if these values of F were significantly different from the, 0.017, 0.019, and 0.016, that I estimated at the very beginning, not knowing the discharge rate and the velocity and the Reynolds number. I would have to just simply take these numbers and work the problem again. And even the KY pipe problem, computer software package, that's what it does. It does it iteratively. It goes through an analysis, it computes the discharge, it checks, and then it does the computations over with another value for L. Hayes and Williams is a moot point because Hayes and Williams doesn't let the roughness coefficient be a function of pipe characteristics anyway. And this second of three examples, and a good stopping point might be to run through these examples and then take a break. And so there's two more. This is the second of the three, in which we've got two pipes in parallel. This is just a little piezometers. This is how high the water would rise in a piezometer, and how high the water would rise in the piezometer is just saying that the difference in head between those two locations is 25 feet. And the diameter and the length of the pipes and the roughness and all is already computed in the K values. I actually made a little table at the bottom that gives the length, diameter, area, friction factor for the pipes, and I computed the Ks. But at this point, once you know pipe characteristics, you can reduce those down to your Ks. Head loss is K times Q squared. We're using the Darcy-Weibach expression for K. We want to compute the discharge in the pipes, the flow rates in the pipes, for that head difference of 25 feet. And so we apply a bit of ingenuity and using those basic relationships. And again, we can both look at the diagrams without me actually putting them on the screen here. But pipes 2 and 3 are in parallel. If you got pipes in parallel, the head losses are the same. And we can plug in our expression for the head loss as a function of the discharge rate in each of the two pipes. Plug in the Ks, and what that gives you is that the discharge in pipe 2 is just a constant times the discharge in pipe 3. And I see I made a typo that we got to fix. This superscript 3 should be a subscript 3. So be sure to fix that in your notes. And also, pipes 2, the discharge in pipe 1, if you look at your diagram, is equal to the flow rate in pipe 2 plus the flow rate in pipe 3, except we know that Q2 is 2.145 times Q3, so we can plug that in to say, get an expression that relates Q3. I did it again, didn't I? Made another typo. And so Q3 is 0.318 times Q1. Excuse the typos, please. That subscript 3 should be a subscript 1. Okay. Doesn't matter which route we go. One route would be pipe 1, pipe through pipe 1s, 4, and 3. You could do the same thing by going through pipes 1, 2, and 3. But either route, from one piezometer to the other, and the route I took was that route, so the total head loss is the head loss in 1 plus head loss in 4 plus the head loss in 3. And that's going to total to 25 feet, the difference in the head. And so we plug in, for each head loss, we plug in KQ squared. And then we've got values for the Ks. And I see I didn't actually write them in, but if we know each of the Ks, so we plug in the numbers for the Ks. And a couple of the pipes have the same diameter. Notice that pipes 1 and 4 have the same diameters, and because they have the same diameters and because they're in series, they have the same discharge. Everybody agree that pipes, well, they have the same discharge period. Pipe 1 and 4 are in series, so they have the same discharge rate, and so Q1 is equal to Q4. And we know that Q3 is 0.318 times Q1 from that computation. And so we can plug in a Q1 for Q4. We can plug in this expression for Q3. And having done that, the only unknown will be Q1. And so we get a Q1 of 4.47 cubic feet per second. Q4 is equal to Q1 of 4.47 cubic feet per second. And then we can go up to this expression, knowing Q1, plug it in to get Q3. Go back over to this expression, knowing Q3, plug it in to get Q2, and we got the flow rates in all the pipes. And so this type of problem can take all kinds of formats. And this third and last example on this this line of thought is computing the discharge in each pipe. And this time we've got 3 pipes in parallel. We know the discharge coming in, we know the discharge going out. We want to compute the discharge in each pipe. The K's are given. The K's came from the Dorsey-Weibach, so that means that the N is going to be 2. And so looking at the diagram, you know the total head loss. I've left off another subscript, so let's put in a 1 here. And the head loss in pipe 1 is equal to head loss in pipe 2, which is equal to head loss in pipe 3. The expression for head loss is KQ squared, so plug in KQ squared for each of the pipes. And I'm not sure what happened to my subscripts here. I'm having subscript problems. Got to fix that too. That should be subscript 2. Sorry about that. And then you can manipulate these expressions to get the flow rate in one pipe as a function of the flow rate in another pipe, as shown here, and then recognize that the total flow, the 12 cubic feet per second total flow, is the flow in the first pipe plus second pipe plus the third pipe. They're pipes in parallel. And having expressed the flow in one pipe as in terms of the flow in another pipe, we can, for Q2, plug in Q2 as a function of Q1. For Q3, plug in Q3 as a function of Q1, and that leaves us one unknown, the discharge in pipe 1, which we can solve to be 3.30 cubic feet per second, and then plugging that back in to this expression to get Q2, and then plugging Q1 back into that expression to get Q3. We've got the flow rates in all the pipes. And I guess to check our arithmetic, we ought to go ahead and add those 3 numbers up, and they better add up to 12 cubic feet per second. And so that's sort of applying those basic concepts with a bit of ingenuity to look at flow, the way flow divides between pipes. And what we need to look at after the break is to expand the basic concept so that we can analyze a pipe system that has 1,000 pipes in it. And that's where we're going next. And you've been sitting a long time, and I can talk forever. So how about a break? Need to stretch your legs, restroom break, or whatever? How much time do we need?
Take a few.
5 minutes, long enough?
5.
Or whenever whenever y'all both get back, we'll start again.